If you put times 10 in your calculator, though, you got to keep track. You got to be careful of that. Okay, we're on chapter 17. We're going to do this sound question right here. And 60 decibel sound is measured at a particular distance from a whistle. What is the intensity of this sound? So we know, hopefully, my decibels is equal to 10 log of my intensity over my intensity Sabot, which is my 1 times 10 to the minus 12 watts per meter squared.
So that's always a constant.
This right here is a constant, yes.
That one we had yesterday. Always.
1 times 10 to the minus 12.
Well, I was thinking, I thought it was just like that problem. I didn't know that was a constant. Did you ever say that was a constant? Is it? Yeah, sorry, go ahead.
Okay, so if we have a 60 decibel sound here, then this right here is 60. If we divide both sides by 10, we're going to have 6 is equal to the log of I over I sub O. Let's leave it like that for now.
How do you know when to divide by 10?
Because I want to get rid of this 10 right here. I want to get log by itself over here. So once I get log by itself, and I did a little proof of this yesterday, I think. I did a side note here. So if you have 2 is equal to the log of, let's see, 10,000 over 100. So we have something that kind of looks like this, right? We've got 2 equals the log of a number over a number for I over I sub O. Yeah, I divided both sides by 10. I'll put this in red. Okay. Now, check this out. If I take the inverse log of both sides, 10 to the 2 is equal to 10. Don't write this down. I'm just proving this. I don't think so. So if you take the inverse log of both sides, is this equal? Yes. So you'd have 10 squared is equal to 10 to the log of 10,000 over 1,000. This just becomes 10,000 over 100. And then you still end up with 100 equals 100. So my point is this: if you take the inverse log of a log, you can bring this out by itself. But you have to take inverse log of both sides. What is inverse log? 10 to the x. So in your calculator, if you go the log base 10 of 100, it's going to give you a result of 2. That's saying that if you hit inverse log, it's saying that 10 to the 2 is equal to 100, right? It's returning this number. So you can go back and forth. You hit log of 100, you're going to get 2. If you hit inverse log of 2, you're going to get 100. So
What is the inverse log button?
it's a log button. It's just, yeah, you got to hit, since this is light yellow, it matches my second color here, so. So this then, we're going to go 10 to the 6th is equal to 10 to the log of I over I sub O. That means 10 to the 6th is equal to I over I sub O. then we know what I sub O is. So my intensity is going to be I sub O times 1 times 10 to the 6. This is 1 times 10 to the 6. We can put it that way. Right? 10 to the 6th is still 1 times 10 to the 6th. So here's my I sub O number. So that should come out to be our intensity. Yeah, 1 times 10 to the minus 12. And you can do this. You don't need a calculator for this. If this is a 1 and this is a 1, we could add the exponents. Negative 12 plus a 6 is negative 6. We should get 1 times 10 to the minus 6. Okay. Can we do some Doppler? Anything else? What, Emily? This has got to make sense. This has got to make sense. There's a lot of variables, yes. Oh, here's what I'm going to do. We have got, I'm telling you to use common sense on this. I'm not going to give you, because if you do the plus and the minus, that's 2 equations. If you do the plus and the minus here, that's 2 equations, but they could be this and this. There could be 16 equations here, maybe. 8 equations. I'm not going to give you 8 different equations to solve for this. You are going to have to use the minus or the plus or the minus or the plus correctly using common sense. We need some common sense to take over here now. I'm going to write down this YouTube video. I'm going to teach it the common sense way. I'm going to, first of all, we looked at this yesterday a little bit, but we were at the end. I'll actually show you this quick first. So I'm going to turn this up.
The wind moving up from a
Oh,
stationary
sorry.
source travels equally in all directions.
I have a solution for that too, finally. Yes. For some reason, VLC is the best media player I've ever had, ever known, and all of a sudden, well, let's do this one first. We looked at this yesterday. That's just nothing's moving, right? The source is not moving, the observer's not moving.
The rate at which waves are sent out by the source is the same as the rate at which they arrive at the ear.
So if the tuning fork's 200 hertz, they're going to hear 200 hertz.
As the source moves toward your ear, you'll hear a higher pitched sound.
The waves are entering your ear at a faster rate, correct? Moving source, moving source. We have our own equation for that.
As the source moves away from your ear, you hear a lower pitched sound.
So the waves are not going to enter your ear at the same rate, right? Less rate wise.
listener moves toward the sound, its apparent frequency increases. As the listener moves away from the sound, its apparent frequency decreases.
Now, here's where some examples. This is a moving source stationary observer. So when this train comes at the person, they're going to hear a higher frequency. When the train passes, they should hear a lower frequency. Moving source, the train whistle is the source, right? Moving source, stationary observer. Moving source, stationary observer, car horn. You could definitely hear that change when it passes. Moving source. Moving observer. The camera is on the train is moving. This is not the train making the noise, it's the crossings, right? The crossing gates. You can definitely hear that change. Now I can show you that with this simple device. Where's that thing right there? I don't know if this is going to show up. I think you're going to be able to hear it. So this is going to put out a sound, and I'm going to swing this in a circle. So where is that thing at? Like this? Well, I don't know. So it's definitely putting out a frequency, correct? Now, as a student once told me, nothing good can come out of this. And I crashed and burned, but this tone is changing, correct? When it's coming at you versus going away. Because that's the same, right? It definitely is changing. So, let me just go to, yeah, it's working fine. Coming at you, higher, 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 every time it comes through that bottom loop. Ooh, that thing's not a good frequency. Ooh. One more I'll quick show you. Essentially, this is the same thing.
The wave moving out from a stationary source travels equally in all directions.
This is just plopping water in a water tank.
Notice how the wave fronts appear to pile up in front of the moving source and seem to spread out on the back side of the source.
Higher frequency in front then, right?
More com-
Now the speed of the source is 7. The speed of the wave is...
On the front side of the moving source, the waves are closer together. On the back side of the moving source, they are farther apart.
This demonstrates breaking the sound barrier is what they're going to demonstrate, because when that source wave moves...
The speed of the source is about 3/4 of the speed of the wave. Notice how the waves are beginning to stack up on the front side of the source.
You see, can you see this darker V forming right here? This is your shock wave. So when this source moves faster than what the waves can move out of the way, then essentially that's the same as breaking the sound barrier. And they think they show that here. So you're close. Here's 18. This source is 18. The wave can move out of the way at 19.
The source is traveling at 95% of the speed of the wave.
Here's this.
Notice the buildup of a front of waves on the forward side of the source. The source is now moving at 105% of the wave speed. Notice the buildup and motion of a shock wave.
Here you'll see it
Shock wave
right
moves
here.
off at an angle determined by the speeds of the source and
Here's
of
your
the
shock wave.
A shock wave moves out from the source.
So you can see
Draw
that.
a circle around the source.
All right, let's tackle this equation. Again, common sense. We're going to use common sense to do the plus and minus with common sense. So, we're going to do, we'll do an example here. We'll say the velocity of your car is 60 miles an hour. We'll do the car example. $60 miles per hour. Let's change that to meters per second. So the quick way to do that, we'll make this 3,600 seconds. Yep, 60 miles per hour. You know, I'm just making this up. 60 miles per hour, and then we'll go 1 mile. What did I do? I guess I did it in feet. 1 mile. How many feet? 5,280 feet. And then how many feet in 1 meter? You got her. 3.281. .8 meters per second. Okay. For A, you, like that person, therefore, if you are standing on the side of the road, the velocity of the observer is 0. You are the observer. The frequency of the car horn is 420 hertz. What will you hear? So we'll do A here, I'll do a B over here. So we'll try to do this if you're kind of in the same territory. So here's the equation. The frequency of the observer, you're the observer, you're going to hear, is going to equal the frequency of the source, 420, times the velocity of sound. Now, velocity of sound, this is the V. Velocity of sound, notice it's the same number in both, correct? Now, typically, well, let's do 20 degrees. Let's say about 20 degrees Celsius. Velocity at 20 degrees Celsius, what should we get? What's the formula? Same pressure. Yep, sorry. Velocity of sound at 20, what do we use? Yeah, 331 plus, what's the number? What's the number? Yeah, 0.6 times our temperature of 20. That's going to add 12, huh? 343 is typically a number we'll use. That's, yeah, that's just standard equation. That's your adjustment. No. So we're going to use 343. So this number here does not change. I'm going to put this in black. 343 meters per second over 343 meters per second. There's my V over V. Now we got to do the plus or the minus. Now, if you remember this equation, the observer stays on top, source is to the bottom. Now, is our observer moving? No. So for this, we're not doing anything, we're not adding, we're going to have a 0 there. Our observer's not moving. Now here's the common sense part. Our source is moving at 26.8. 26.8, yes. That is the velocity of our source, right? Now, if this source is coming at you, should you hear a higher frequency or a lower frequency? You should hear a higher frequency. Now here's your common sense. First of all, your common sense is you should hear a higher frequency. Your next common sense comes in mathematically. Mathematically, if you want this number to go higher, do you want a proper fraction or an improper fraction? Do you want the denominator larger than the numerator or smaller? All I'm attracted. I don't care which way it's moving. All I want you, let's go back to your first observation. The frequency heard should be higher, correct? We need to get this number higher. But the observer's not moving.
If the source is moving toward observer, use negative in the denominator.
We want an improper, this number right here, listen, if we want this to go up, this has to be greater than 1, correct? This result has to be greater than 1, which means we need to lower the numerator by 26.8 meters per second.
Say the bottom is like the distance between you and
Distance?
model the velocity distance to subtract the velocity increases the distance that so really that bottom number is the distance between
I wouldn't say distance. What are you going to do when it's moving away then? Punch this in. Yeah, it's almost reversed, but you could come up with some way like that, I guess. What do we get for a frequency? $455.6 hertz. Okay. Now, what if we did this? What if we did U in moving car car horn at intersection, and you're moving at 26.8. Let's see, you in a moving car at 26.8, car horn at intersection, blowing at, we'll do 420 hertz. You hear what? So you're in the car. Your car horn is not going, correct? There's a car horn going at the intersection. What are you going to hear? So we'll set this. Why don't we do both? I was waiting for that question. We're gonna put both into this.
Because I was thinking that when you were talking about the train, because the train when it's coming at you, that horn blowing at you, it would just
Yep. So we're gonna do both. So I was waiting for that question. Yes, I was perfectly. 420 hertz. This is gonna stay the same. 343, 343. Now, who is moving, the source or the observer? The observer is moving. But down here, it's going to be 0, right? Source is not moving. Now, we have the opposite over here. We need to stick that number in the numerator. When I do I'm going to put plus and minus both in here. And I'm going to keep track of this. 26.8. We don't need any distance. No distance in this equation. Now, for the plus, when we add it, is it going to make the 420 go up? Now, just think proper and improper fraction. First, let's review that math-wise. If you have an improper fraction, the numerator is greater than the denominator, it will produce this number here that's greater than 1, correct? If you want this number to go up, this result here has to be greater than 1. So when you're moving towards this 420 hertz horn, you should hear a higher frequency, correct? So this would be toward, and the minus would be away. Right? And now, let's see, if you're moving toward, you should get 452.8. I kind of got, you're going to hear 452.8. Here's my answer. And when you're moving away, you're going to hear what? 387.2. Anybody else punch that one in? I don't have that one. 387.2. Okay, good. That should make sense, right? Moving towards you, you're going to hear a higher frequency. Once it passes, you're in the car listening, you're going to hear less. Notice, math-wise, these do not match. So you're not going to get the correct answer. It's not the same effect. Okay, let's go to the next page. And on the next page, we'll do a train horn quick. Let's see if we can tackle both of these. Let's see. Train's doing 100 Gent. Speed of sound is 340. Train, what frequency observed by a stationary person? So the velocity of the observer is 0 when it approaches and after it passes. Here's my train. I better put some boxes in my train, put some wheels on my train. It's a nice looking train. 150 hertz, right? Stationary observer. Velocity of my observer always equals the velocity of the source first, 150 hertz. Ratio now, my speed of sound and air, in this case 340 and 340. Now my observer stays on top. That's a way to remember this. I'm going to put my plus minus. I'm going to put my plus minus. Let's see what I'm going to do. What's moving here? Okay, so my observer here, and my observer stays on top. Is my observer moving? No, so I'm going to put 0. Oh, crap. Well, I know this is 35. Now, the question is, when's the plus and when's the minus? Now, is the plus going to make the frequency go up or down? Let me ask you that question first. The plus is going to make the 150 go down, correct? Because this number here is less than 1 once you make that denominator bigger. So then, since this goes down, this plus is going to be for what? This is going to be away after pass, right? After it passes. And the minus would be toward or before passing, right? Toward before passing. So they would hear (167.2 hertz) toward, and 136 hertz away.
You always have to solve it before you solve it.
You could. No. But you don't always have, usually you're only solving for 1. Now, B. What frequency is observed by the trained person? They're just in the train, right? They're not going to hear any difference. It should be the same, right? I've never ran into a trick question as a teacher in my life, ever. I've never written a trick question. No trick question there. Okay. Now, this is big in ultrasound now, is vascular. They've come a long way in 3D, and vascular is all blood flow. So we know a sound above 20,000 hertz or 20 kilohertz is above the highest audible frequency, ultrasound. This frequency is 2.5 megahertz. 2.5 megahertz. That is how many hertz? There's a couple ways to do this. Mega is 10 to the 6th. This is 2.5 times 10 to the 6th hertz. That's what I'd put in my calculator that way. Or you need 2, 5, and you just keep adding zeros. 3, 6. So that'd be 3. Yep, that's 2.5 million. It'll look like that. Now, if your heart's pumping and if there's a constriction, it's probably going to force that blood through that constriction at a faster rate. But here's what we've got. Blood's moving at 20 centimeters per second. The speed of human tissue is, through human tissue, is 1540. Ooh, accurate to 7 sig figs. We want to figure out what is observed by the microphone or the probe. So the microphone would be a stationary observer, correct? And the blood is flowing towards that.
How come the blood is moving toward
We could do it both ways.
it's an artery session?
Should be away? All right, we'll do it away. Say, all right, so blood flow away. So we are going to do the same equation. The frequency of the observer, which is going to be the probe, microphone probe, is going to equal the frequency of the source, and that source is 250,000. This is supposed to be to how many sig figs? 7. 1, 2, 3, 4, 5, 6, 7. And I'm going to put a decimal point there. That means all those numbers are significant. And this is our 1540 over our 1540. Remember, that stays on top. So I'll continue to put in my plus minuses. This is my probe or my microphone. Is that moving? No. So there's where my 0 is. Now, if the blood is moving away, should this frequency go up or down? This should go down. If this needs to go down, am I going to add or subtract? I need to add. So this is plus, how many meters per second is 20 centimeters per second? Yeah, this is going to be 0.20 meters per second. So what do we get for that? 2.5 to the 6th times 1540 divided by 1540 plus 0.2. I get 24,99675. No, we got to do this to all those sig figs, right? All these sig figs. So we get 24,99675 for an answer.
What would it be, 8, 0? 6.
I think that's 7, and then, you know, all of these, all of these would have to be, it's really not realistic, but I guess the machine would pick up a difference. Okay. Now, let's start our drawing up here. I need you to do a nice drawing up here. We are going to do open and closed pipe resonance. So we need a really nice drawing here of a straight, we need a straight line like this. Mine's pretty straight. I don't know what yours looks like, but I think mine's pretty straight. We're going to end about right there. And we have a closed pipe. Leave a little bit of room right here. And I'm going to make this as straight as I can. Now, to get this to match, I'm going to do 5 ticks. 1, equal distance. 2, 3, 4, 5, like that for now. Can you make equal distance 5 ticks? We are going to try to center a wave through here. So we're going to do a dashed line right down the center. Now, we got at least 5 ticks. How much do you have left here? Okay, so let's start the wave here first. Now, here's what's going to happen. We're going to send a wave This is my musical instrument here. And you're going to do this for lab. We'll calculate the speed of sound in lab Tuesday. And I'll be shocked if anybody is off by more than 5%. I don't think you can get off by more than 5%. There's no way. It's very accurate. You can't do it. You can't get off by more than 5. This right here is an open pipe. It's just an open piece of glass. When you do the lab, let me zoom out, excuse me. So if I plug this with my hand, I have no idea if this is going to resonate, but I'm going to send a wave into this closed pipe because I closed it with my hand. Not the right frequency to resonate. What is this? I have not pre-calculated this, so there's a little bit there, right? There's a little bit there. So here's what happens. We are going to you need a different color for this. We're going to get this perfect before the end here. This is going to be this color. So this, we're just doing this for this one right here. Then we got to come down. I got to make sure I don't screw this up. So then there's going to be a wave down here. That's going to be at the bottom here. And then it's going to go to here. So then we need this. And we'll go to the top here. Yeah, we want the same. We just got to go opposite here. So did I already kind of mess that up? Did I go? Oh, I think I just stretched it out. Let's go with the other color here as best we can. Now you need a different color to go opposite. I think I'm all right. Now that's what I've got so far, 2 different colors. So this has to come down here like this. I think I messed up. Ah, crap. Yeah, this should have came up to here, right? So my blue wave got that messed up. And the only way to fix that is some whiteout. So, we'll fix it up next time. Let me show you what I have done. Okay? This is what happens. This has to have constructive interference in this. This will make sense now. Remember I did that standing wave with the surgical tubing, right? So here's what happens. There's an incoming sound wave that's in my blue. It is going to reflect off this closed pipe end, correct? Then it's going to send a wave back. My bounced off wave is in red. That's how we can get standing waves in there. You have to have the right frequency coming in and the right length to have a good musical instrument, depending upon what frequencies and all that. That's what we'll discuss next time we meet. Yes, depending upon the length of the tube and the frequency that's going in. Now, for your quiz, well, if a question has Doppler on it, you can do it, right? You'll be able to pick up a Doppler question on the quiz and the homework. The homework's plain as day for Doppler. Okay, we will see you guys next week, huh?